All right, let's look at the Taylor polynomials assignment. We've got 6 questions, so let's go right into it. So here we are trying to find the Taylor polynomial t sub 3. So we are going to go out 3 derivatives in our computation here, and we want to be centered at x equals, or a equals pi over 2. So we should look like the cosine function of pi over 2 when we graph, but before we even get to graphing, what are we going to do? We're going to take the original function, its first derivative, its second derivative, and its third derivative, and evaluate them all at this a. Then we're going to take each of those derivatives and divide by n factorial, where n is the number of derivatives. So 3 factorial would be 3 times 2 times 1, or 6. 2 factorial would be 2 times 1, or 2. 1 factorial would just be 1, and 0 factorial is 1 by definition. Then, taking those coefficients that result when we take our derivatives evaluated at pi over 2 and divide by n factorial, those become the coefficients of a polynomial. Now, because the polynomial is centered at pi over 2, it's not just going to be something plus something x squared. No, it's going to be something, namely your degree 0 coefficient, plus your degree 1 coefficient times quantity x minus pi over 2. Then you're going to have your degree 2 coefficient plus quantity x minus pi over 2 squared, and so on. And that's the nature of things here. Because we're going up to t3, you're going to take that degree 3 coefficient, the one that resulted from the third derivative evaluated pi over 2 divided by 3 factorial, and that's going to be parked in front of x minus pi over 2 cubed. So it's going to be an ugly expression. It's going to be really long to write out, but so be it. It will be what it is. And it should look a hell of a lot like the cosine function at pi over 2. So the cosine function at pi over 2 is like, where is it? Down here, right? And so this is looking good, actually, right here. Because, well, maybe that's it as well. Oh, geez, that's looking pretty good as well. So maybe take, well, oh, no, this can't be it, because the cosine function goes through 0, 1. So it's got to be one of these two. It's not going to be this one, because that blue function does nothing like the black function. But yeah, looking at these two examples, hard to say which one it's going to be. Maybe sketch a graph in Desmos or something to see exactly which one it is, because those look pretty close. I guess if we're letting the black one be our cosine, or is the blue one being our cosine? It doesn't even say. It doesn't even say. Fun. Okay, well, do your best to try to parse this out. I would recommend getting a picture from Desmos. You can just take your expression here for T3, take your cosine x and graph them. When you graph them, it's a beautiful picture, so I certainly recommend it. Okay, what about the next one? Here we're doing ln x at a equals 1. Also T3, so we're going out to the third derivative with our computation. So first thing, what do? We take original function, first derivative, second derivative, third derivative. Be careful with your negative signs here, because they come into play. Then, what next do? We take those expressions for f through f triple prime, and we evaluate at a equals 1. Now, fortunately, that's not too terrible to evaluate at in this case. And once we evaluate, we're going to get some numbers, whatever we do. What do? We divide by n factorial, where n is the number of derivatives. So the third derivative evaluated at 1 is going to be divided by 3 factorial. The second derivative evaluated at 1 is going to be divided by 2 factorial. Remember, 3 factorial, 3 exclamation point, is 3 times 2 times 1, or 6. 2 factorial is 2 times 1, or 2. Okay, now, once we get those coefficients, there's going to be 4 of them, a degree 0, a degree 1, a degree 2, a degree 3. Now we're going to throw those into a polynomial. But that polynomial is going to be centered at a equals 1. And so instead of just being the 0th degree coefficient plus the first degree coefficient x plus the second degree coefficient x squared, no, we're going to have the 0th coefficient plus the first coefficient times x minus 1, and the second degree coefficient times x minus 1 squared. So each of the expressions that are increasing in degree are going to have the expression x minus 1. And so ultimately what results is a cubic function that looks a hell of a lot like ln x near a equals 1. So this looks pretty good, because it looks like ln x is right there, and it looks like your degree 3 might be there. That's not ln x. That's ln x, but that doesn't approximate it well at all, and that's not ln x. So this one's very straightforward. Going to the one above then, I'm going to assume that the blue function is the cosine. If the blue function is the cosine, it's still one of these two. Which one it is, I don't know. You'll just have to look at it, because that looks curved to me. That could be the degree 3. I don't know. Again, use Desmos on that one. That's a little bit stifling. Okay, calculate the Taylor polynomials T3, T4 at x equals a for the following. So we're doing it x equals 8 at x equals 4. So how do you do T2? Original function, first derivative, second derivative. Evaluate all of them at a equals 4. Divide each of them by n factorial, where n is the number of derivatives. 2 derivatives divided by 2 factorial. 3 derivatives divided by 3 factorial. Well, I guess you didn't do 3 derivatives there. 1 derivative divided by 1 factorial. Remember, 0 factorial is 1 by convention. And then you take those coefficients and you're going to cook up a polynomial where instead of x, x squared, and so on, you're going to have x minus 4 squared, and so on as the variable-based expressions within the polynomial. It's a weird way to cook up a polynomial, but if you FOIL it out, it'd be a polynomial anyway, so be it. But doing it in that way is the most convenient way to express a Taylor polynomial, so that's what we do. Right, T3, you're just adding one additional term to what you did in T2. So take the now third derivative of f, evaluated 4, divided by 3 factorial, and put that as the coefficient of x minus 4 cubed. Add that to whatever you had in T2, and you can see that T3 is a literal extension of T2. It just has an extra term to consider. Now, when we talk about Maclaurin series, or Maclaurin polynomials, we are talking about Taylor polynomials centered at 0. So here, each of the terms x minus 0 squared, and so on, are the classic expressions for polynomials that we are familiar with. X minus 0 is just x, and so yeah, you just have x, x squared, and so on. Now, to determine what the Maclaurin polynomial is, I encourage you, write out a few derivatives, evaluate at x equals 0, because we're doing the Maclaurin polynomial, and then divide by n factorial. Dividing by n factorial is going to give you the appropriate denominator, and you'll see that one of these expressions, I think it's the second one, turns out to be what we end up with. But don't take my word for it, because I haven't gone through the computation. Here, we're doing a similar thing, the Taylor polynomial of this guy. Now, as you start writing him out, there's going to be a trend in the expression of that polynomial. And keep track of the trend, what you get when you compute f prime, and f double prime, and f triple prime, and f quadruple prime. And then you're going to divide by 0 factorial, and 1 factorial, and 2 factorial. And then you're going to take those numbers that result, and you're going to put them in front of x minus 1. And, well, first you're going to have a constant term, and then you're going to have the degree 1 term in front of the degree 1 coefficient in front of x minus 1, and the degree 2 coefficient in front of x minus 2, or excuse me, x minus 1 squared, and so on and so forth. And so, yeah, you'll get something here, and I believe there is going to be alternating signs here, so this minus 1 power is going to come into play, and you have to be considerate to whether or not we have n or n plus 1. You have to think about what the sign is on the nth term. If n was even, do you get something positive? If n was odd, do you get something positive? Ask yourself those questions. You'll be able to deduce which one is accurate. Yep, finally, oh, this is a classic. I've seen this on a test before in another institution. Compute T3 for f of x equals square root x centered at a equals 4. So you're going to have to compute first derivative, second derivative, third derivative, fourth derivative, well, not fourth derivative, just up to third derivative. Then you're going to evaluate all of them at 4. Then you're going to divide by 0 factorial, 1 factorial, 2 factorial, 3 factorial, respectively. You get coefficients. The 0th coefficient is by itself. The first coefficient goes in front of x minus 4, because we're centered at 4. The second degree coefficient goes in front of x minus 4 squared, and, well, you only have one more coefficient. The degree 3 coefficient goes in front of x minus 4 cubed, and that is that. So this is the beginning of a study of Taylor approximations by looking at Taylor polynomials. In a future section, we're going to power these polynomials up, not stopping at t equals 3, not stopping at t equals 2, not stopping at t equals 10 or even t equals 20. Just let t go to infinity. You would get sort of like a supreme approximating function. And, well, that's really why we even study the infinite series that we are about to in the next section, because we want to know how to get a grapple on a sum of infinitely many terms, because a Taylor polynomial that would be extended forever would be an expression with infinitely many terms. We want to know the behavior of that, when that is meaningful as a real number, when it's not. And those are the types of things that we are sort of working to here. So that's probably more than you bargained for with that insight, but it's nice to have, it's nice to know, and, well, hey, that's a discussion.